Today we're going to look at this topic. This is the basic models, modeling concepts, and we would look at the basic elements and the constitutive relationships of each. So let's get started. And we see here a set of different elements in different energy domains, like and this is a mass in here that is moving to the right, and the way we express the power for this kind of, for the physics of this is the force times the velocity. If you have this little circuit on the right hand side, power is also voltage times current. On this rotational system, it is torque and angular velocity, and in this hydraulic system, it is the pressure and the volume flow rate. So these are the so-called system variables. In the way we use to represent each of the elements and the interaction with the other elements on the system is through these system variables. The the either force and velocity, torque and angular velocity, and voltage and current. This is we're going to name these variables. In general, you see how this one at the bottom is in here that says that um, you have this effort variable and the flow variable. This is the family of variables. You can say this force and the torque and the voltage and the pressure, they are the so-called effort variables. But this one, this velocity, angular velocity, current, and volume flow rate are these flow variables. As I mentioned to you, Professor Painter at MIT in the 1950s came up with this idea that we could classify these families of variables, reduce them to this two, this effort and flow variables, and generalize in such a way that we could represent systems in many energy domains with the same variables. So for example, all the efforts, if you have a mechanical system, it would be measured in newtons for the force, in voltage, in volts for the voltage, Newton meters for the torque, and newtons per meter square for pressure. And the flow variables would be a velocity in a mechanical system, a current in the electrical system, angular velocity on a rotational system, and volume flow rate in a hydraulic system. So this is in the different energy domains. Now, if we generalize these so-called power variables, we could also come up with this so-called tetrahedron of state, which Painter invented to represent the four variables that we use in this notation. The effort variable and the flow variable are here, and he says that if you differentiate this variable, this momentum variable, you obtain if you differentiate the flow variable, you obtain this Q. Or you could say it the other way, that Q is the integral of FTT. That's another way of saying it. But this is just a little diagram to illustrate all those four variables. Now, what do I mean with these four variables? Take a look in here. In a mechanical system, anything to do with forces, and this is measuring newtons, torque, voltage, pressure, all these guys are one family of variables, the same type of variables. This other one, velocity, angular velocity, current, and volume flow rate, these are also families of variables that in different energy domains, we're going to call them flow variables. The integral of the flow variable is called the displacement. You know, like the integral of the velocity is the displacement. Well, this is measure displacement or angle or charge or volume. This family of variables is under the displacement, or we call it Q variable. So this we're gonna use the letter E, F, P, and Q. So maybe it's worth me making some notes about it, so that, see here we're gonna use the variable E over here. This we're gonna use the variable F. The displacement we're gonna call it Q, and the momentum we're gonna call it P. So these four variables that you see here, these are the system variables, or we are gonna call them generalized variables. Okay, so this is the way we are going to use these four variables for different things. So in here, if we go and now represent things with these variables, and we begin assembling a system, you can actually do it this way. See here, for example, this is the battery, and as you start your car, the motor starts, by the battery giving a charge to this, and then creating a torque that actually starts your engine. So in the past, after Painter and Professor Carnop, the author of your book, and they made it easier to understand this, that you could actually lay out the elements of the system and just connect them. But you see, each connection has those two variables, the E and the F. In this case, voltage and current, and after the motor, torque and angular velocity. So, having done this, you have the ability to create models of systems that are, quite significant. Like, for example, in this case, you have the model of a vehicle. You have the engine first in here, and then you have the clutch, you have the gearbox, you have the drive shaft, the differential box on the side over here, and you have each of the wheels over here. So isn't it neat? In here you have the entire vehicle as if you would have laid out the elements and simply connect them. But laying out the elements and putting names to it and simply connecting them is not going to produce computer results. So we need to identify with certain symbols each one of these elements, and then do the connections and expect that the system is going to work as a set of elements interconnected with each other. So that's why we're making it easy right now to get it started, but in reality, we have to give some names to each one of these components, and that's what we're gonna do next. So, do we have any questions?
Yeah, what does Bendix mean?
Bendix?
BENDIX.
From the previous slide.
From the previous slide. This is a word used for the little gear on the starter of your car that connects with the flywheel, and then starts your engine. Okay, now it comes to this concept that we talked about, and I want to emphasize this again. We have in here on the top, we have the representation of this using a block diagram. If two elements of a system, element A and element B, are connected with each other, they exchange information as a system works together. They exchange information through those variables, like the effort variable and the flow variable. But on the right-hand side, on the left-hand side, we have a little difference. And can you see what it is? In this particular case, in the case on the left-hand side, let's see, where is the left-hand side? Right here. Case of the left-hand side, this element A, C acts on B and sends the effort, but B reacts with the flow. In this case, on the right-hand side, B sends the effort to A and A responds with the flow. Remember the so-called cause and effect? Well, here it is. This is the element A. Now, if we represent the same thing as up here with this notation that we did in the previous lesson, this is the element. This is as if you hold it with your hand and push it with this. Let's call it a tool. It's very obvious that you could with this end you could push something. So let's look at that way. Sort of figuratively say that if you actually let's try this. This is as if you had, let's say, your hand in here. I'm gonna draw your hand right there. Hold it there, and now you use this as a tool. It's very obvious that it would allow you to push it this way, right? So this is the element. If you do this, isn't it true that this is the output? And then this is the input. Yeah? So you have that is the element, effort comes out, flow goes in, which is what this means. In this other case, you have this element A, effort goes in, flow goes out. So this is out in here, and this is in, the input in this case. So you have either this representation or you have this representation. All right. Having said this, let's go to the basic elements in here. You have in this chart 9 elements. And what I'm here to tell you is that with these 9 elements, we should be able to model just about anything in real life. And here you have the 2 sources in here. You have 2 connectors. Right there is almost half of them. And then you have this 5 elements. 1 element that will store kinetic energy, 1 element that stores potential energy, 1 element that dissipates energy, and 2 elements that transform energy in one way to another. In this case, for example, the transformer is just like a like a gear set, but there's a different kind of transformer, you may say. This is like an electrical motor, where the effort variable is not related to another effort variable, but rather to a flow. Like in an electrical motor, the torque is related to the current. And then you have the angular velocity is connected to the voltage. So you have, we have the 9 elements consist two sources, two connectors, two different ways of connecting things. One element that stores kinetic energy, one that stores potential energy, one that dissipates energy, and two transformers. One that transforms an effort into an effort, flow into a flow, and the other one that is, we could call it a cross transformer, which does one effort into a flow and vice versa. Okay, so let's make some progress here with the notation. In this particular case, if you have the element A and you have the element B, this half arrow is going to indicate which way the power flows. See, power flows from A to B here, the power flows from B to A over here. But that mark is independent of this so-called causal mark, because remember, the causal mark is determined by which variable is the output. Yeah, and in this case, you can see that this is the output of A is the input to B, and the output of B is the input to A. Yeah, so that's how we should read this. This, on the other hand, it says that the input to A is this effort, and the flow is this one. Okay. Now, if we look at different ways of assembling systems, isn't it true that this is the system that we used with the Simulink model? If you do a system like this using bond graphs, then you can very easily lay out the elements and produce the simulation, which is the next thing we're going to do.